NASA Goddard, as HP mentioned. Full disclosure, I have like 0 Python skills. So I want to give a shout out to the collaborators mentioned here, Brendan, Gian, and Caleb. They all also work at NASA, but are Jupyter Notebook pros. So I'm happy to chat about modeling, but sadly I'm stuck in MATLAB land. So we'll see how we do with the code here. But yeah, as HP mentioned, I think that modeling is going to be a really critical component of whatever SNOW mission proposal goes forward. So that's why I'm really excited to talk about modeling here today. The 3 learning objectives that I want to discuss, again, just kind of go over the importance of modeling in a satellite mission proposal and satellite mission development. I'm going to provide some sample model output, and we'll explore how to visualize it and just understand the metadata that's associated with it. And then just do some quick examples of comparing our model output both to other rasters and to point-based observations. So hopefully the font is okay on everyone's computer. If not, just give me a shout out and I'll zoom in a little bit. But any future satellite mission, we're interested in getting the best estimates of snow that we can everywhere, right? But a single technology, a single sensor can't do that for all types of snow all over the globe during all times. Each technology has its own advantages and disadvantages. So if we want to get our best guess that we possibly can, we really need to combine all of our options kind of into one mega data product. I think we discussed this a little bit on Monday as well. So in order to combine all of our tools into one place, and things like data assimilation will play a really critical role. And then as I mentioned here, models are also useful for extending information to where we don't have observations. So this is a little diagram that one of my coworkers, Unsang Cho, created and I kind of modified. So if you look on your computer screen, I give an example of what a satellite might see, and you can see that there are big orbit gaps, right? So a satellite might not see everywhere every day, but if we take a model, which we can run everywhere, anytime, and combine them together in a process called data assimilation, we can take that really valuable information that we get from a satellite observation and kind of extend it into those orbit gaps, if that makes sense. So we can take kind of the best of both worlds, combine them through data assimilation, and get a spatial and temporally complete estimate of what's going on. You can do this not only where we have orbit gaps, like in the diagram I show here, but say there's a type of land surface that maybe tends to have really high uncertainty with your satellite observation. If you're familiar with passive microwave remote sensing, that might be dense forests or really deep snow, right? So if we take AMSR2, the observations we collect in those areas tend to have higher uncertainties, but maybe we can use our modeling to increase the robustness of our estimates there. So models and data assimilation are really important tools for taking what we can observe from space and kind of giving us estimates everywhere. So what I'm going to talk about today is using a modeling framework called the Land Information System, or LIS. This is a really handy tool that's really user generated. So within this framework here, I'll kind of scroll down so you can see the image. It's this tool that was developed at NASA Goddard, I think more than 20 years ago now, where it has a lot of different options for land surface models and meteorological data. You can do data assimilation, you can do calibration, you can do a lot of like post-processing, all within this one framework. And what makes it really powerful is that you as the user can choose exactly how you want to set it up, exactly where you want to run it, for how long, whatever. So that's what we're going to be talking about today. Here's our TLDR. Just think of LIS as land surface modeling with the option for data assimilation. So yeah, LIS is really flexible. You can meet your user needs. It runs in parallel, as you can imagine. So we can run over pretty large geographical domains relatively quickly. And then this paragraph here, I want to highlight, there's been a lot of recent efforts in the last 2 or 3 years, I would say, to improve the snow modeling capabilities within LIS. So if you're familiar with land surface modeling, you might be familiar with the NOAA-MP land surface model. It's a pretty common model. It's used in the National Water Model, I believe. And its snow modeling capabilities are okay, but wouldn't it be great if we could use the best of the best? So recent efforts at NASA Goddard and with collaborators have implemented Glenn Liston's snow model and Crocus into LIS. And not only can we run them in standalone, but we actually now can also couple them with NOAA-MP. So that way you can get your really good snow modeling capabilities from Crocus or Snow Model, but also we can get the full suite of land surface models the full suite of hydrological variables from NOAA-MP, for example. So I'm happy to chat about Snow Model if anyone has any questions about that. I think there's probably others in the audience. I know Justin is also familiar with Snow Model. And we're really lucky today that Madi, who's standing in the back and hanging out, he's a pro on Crocus. So we're colleagues at NASA Goddard on the LIS team. So if you have any questions about either model, please stop by, chat. We're happy to help. So let's see. So yeah, as it says here, these more snow focus models can run at much finer spatial resolutions than we usually tend to run land surface models or LIS. And really importantly, they have a lot of tools in them more focused on snow processing, like wind redistribution. They can estimate snow grain size, processes that are really important when we're thinking ahead to a snow satellite mission. So today, the sample model output that I've provided is running LIS with Snow Model. I've run it over Western Colorado, and we can look at SWE, snow depth, and snow density variables. I've run this at 100-meter spatial resolution and for about a 4-year period. But here we're really just going to focus on water year 2020 to kind of overlap with the 2020 field campaign. So here's just kind of a list of what I want to go over in the next few minutes. Yeah, basically understand the metadata and how to understand what variables are in your model file. We're going to do some mapping, some time series plots, and then some comparisons. So before I go on here, does anyone have any general questions about modeling, about LIS, Snow Model, whatever, just before we move on to the code? Like how to get it to run, basically? Sure. So if you need some sort of meteorological forcing data, in our case, well, that's a great question. I think I ran this with NLDAS too, but within LIS, we have a lot of data readers for coarser global data sets like MERA2, GFS. We have readers in case you want to run with like WRF regional climate model data. And then of course you need other initial conditions like your land classification, your elevation, soil moisture, depending on what model you're running, kind of things like that. Yeah. Yeah. Yeah, great question. So all of LIS is actually in Fortran, but there are a lot of tools online to help walk the user how to configure and compile it, how to set up your, we call it our config files in order to say, hey, I want to use this land surface model. I want to run it over these dates, this area. So there's a lot of tools online to help guide the user how to use it. And I think that was one of the reasons that the team was hoping to implement Snow Model into LIS, was that it could maybe be in maybe a more user-friendly place. And so many people don't have to email Glenn and say, Glenn, I don't know how to run this, please help. And now it'll be in a place where we can provide all this documentation. I know Glenn's writing a lot of documentation with it as well. But yeah, it is all in Fortran. Fortran is pretty readable, but if you just want to just run LIS, you won't have to really touch the Fortran. You'll just be able to set up your config file and go. Yeah, great question. Anyone else? Sure. Yeah. Yeah. Yep. Yeah, so this is an example of LIS Snow Model at 100 meters. I would say we've probably tested it down to maybe 30 meters. Madi, I'm not sure how fine resolution you've run Crocus. 100 meters. Yeah, the challenge now we're finding with 100 meters and when wanting to run large domains is meteorological forcing. So if you, like, I know a lot of Glenn's work with just standalone snow model, he'll use met stations. Well, say you want to run all of Colorado, all of Alaska, whatever, or all of CONUS, then we're really limited by our met forcings, and in particular, the winds in the met forcings are really challenging. I would say as a team, we use NLDAS2 a lot. And I don't think NLDAS2 is great, right? Like we need better met forcing data sets. But yeah, we're definitely in the stage where we're also experimenting with that coupling of running both snow model and NOAA-MP at a fine spatial resolution. And Madi's done a lot of the testing as well with Crocus. Yeah. Okay, cool. So now we're in the code. And again, I am not familiar with Python. So if you have code related questions, I am certainly not the person to ask, but we will learn together. So, oh, and let me just say, I'm using the rendered version. If you want to run this in the Jupyter lab, or the Jupyter lab, give it about 10 minutes to run. It's working with some very large data sets, and it's a little bit slow. Probably something I could work on and improve. All right, so we're gonna read in our data, and here we're gonna work with X-arrays. I think Dylan had us working with X-rays yesterday. I can't really remember. But what I wanted to highlight here is that this section, we are actually reading this data from NASA's AWS S3 bucket. And that's one thing that's really handy about using, working in the cloud. I have this data stored with my colleagues at NASA. They helped me set this up, but you guys can all read it. So this isn't even stored on like the SnowEx bucket, but on this EIS bucket that I work on. And that's really cool that we are able to do that. So we're going to pull in our list data, our list snow model data, and then basically we're storing them in X-rays with these. So first, let's go ahead and just, write out the variable, see what we have, see what we're working with. What I want to point out are starting with our dimensions. So in time, we have almost 1,700 days here. So again, this is like 4.5 years of simulation. Then we have sort of our dimensions. You can see they're listed as north, south, and east, west. We'll get to that. That's really not ideal to have them labeled as that. But basically, we're working with a data set that's around 6,700 by 4,800 grid cells. And then you can see our three variables. So again, SWE, snow depth, and snow density. And then if you're not familiar with working with X-array, like me, you can do these handy like dot notation to then see the attributes. So again, just learning more about what does our model output look like? What's the metadata? If you're going to use any data set, it's great to understand it more, just like we mentioned in the last tutorial with understanding the headers. So here you can see our dx and dy dimensions. We're at 0.1. And then you can see we're working in projected coordinates, Lambert conformal. So that 0.1 is 0.1 kilometers. Again, this is a 100-meter data set, not like 0.1 degrees. Excuse me. So then we can also use this dot notation or square bracket notation to look at variables. Here, we're just going to stick with square brackets. And again, let's look at this. We're just going to say, all right, let's investigate our snow depth variable. The way we have this set up, it's all stored in a ZAR store, which from what I understand is a handy way for dealing with large data sets in the cloud. So natively, LIS outputs net CDF files, but I've been told maybe those aren't as nice when you're trying to do quick calculations on the fly in something like a Jupyter notebook. So you can see our data it's chunked, which is fun. But anyway, what I want to mention here is that we can start to appreciate the size of this data set. So we're working with about 200 gigs of model output for our 4-year period. And again, we'll see this as we scroll down. This is only for a small port, like basically just Western Colorado. And hopefully you can start to appreciate as we push towards these finer and finer spatial resolutions. And as we start to think about a global satellite mission, this data is going to add up very quickly. And that's why it's so important to become more familiar with working in the cloud. So this is a good lesson to myself as well, because I don't want to download 200 gigs of data on my local machine, right? I want to work with it in the cloud and do all of my processing there. Oh, and here's my note. Watch out for large data sets. So then this is one part that when I was working through this confused me. I'm not sure if others feel the same way. But when we are working with our X arrays, we can see that we have both dimensions and coordinate variables. One of which it seems like is more of a label for our dimension, and then one is really handy for indexing along that dimension. And these concepts are important when we're subsetting in space and time, because as you can imagine, we don't want to work with this 200 gigs like all on the fly every time that we're trying to do a command. So we need to learn how to subset a model. So you can see one option is to go and just select a specific time. Here's just January 1st, 2020. And you can see when we do that, our dimensions have shrunk to just our north, south, and east, west direction, right? We no longer have a time dimension because we've only selected one day. Maybe you want to select a month here, just looking at January 2020. Now you can see our time dimension has popped back up. We have 31 days. And then importantly, I think we need to think about latitude and longitude. So for the purposes of the tutorial, I don't really want to work with the full data set. It'll just be too slow. So it would be most handy to be able to subset by lat and long. But let me scroll back up here. Lat and long aren't actually one of our dimensions like natively when we're writing out lists. So we need to fix that because that'll make it a lot easier for subsetting our data set. So my colleague Brendan wrote this little function here for working with this. I think Justin has actually written a better function for doing this. So if anyone is interested, let's all chat with Justin and learn how to do that. Basically, this is just adding our latitude and longitude coordinates to fix that problem where our lat longs weren't our dimensions. And once we run this function, we can see, let's output our data set again just to see what's going on. And now we do have our lat long. So I think now we're set up for really digging into this data set and kind of investigating what's going on. Just scroll down. All right, so now we're ready for our spatial subsetting. So again, I mentioned we are just going to look over Grand Mesa for the purposes of this tutorial to subset and work with a smaller size. If you are interested, here is a code. You can go ahead and comment out this Grand Mesa one and uncomment this one here in case you want to grab the full data set. Don't do this on the small server. It'll crash. So just be warned. But anyway, so we're going to subset our data set. And now look, we can see that our latitude and longitude dimensions have decreased as we would expect. So great, we're working with a much smaller data set now. But here it was actually still the full time. So again, let's set now across multiple dimensions. Let's look at just water year 2020. So we're going to do a time slice. Let's look at just the latitude and longitude bounds of this roughly Grand Mesa box that I drew. So we have a lat and a long slice. And now we can just select both our time and latitude and longitude. You might have noticed that we're actually working with two different data sets here. One of which has a TC kind of like appended to it. That's because we actually we chunked our data in two different ways. One is chunked in time and one is chunked in space because each one is better or worse for certain calculations when we're doing them in our Jupyter notebook. So I can try to point out when I notice when we're kind of switching the data sets, but if you're plotting something spatially versus if you want to do some temporal calculations, you might need to have your data chunked separately. There might be a more optimized way to do this, but this is something that we as our list team are still kind of experimenting with and learning. All right, so now let's inspect our smaller data set here. And luckily now we're down to about 1.5 gigs. So this is much more reasonable to deal with than that original 200 gig data set. But you can see, and I forgot to mention, we also went ahead and grabbed only snow depth. So we're just looking at one variable now. So here's our note, much more manageable. So there's a couple of different ways to plot if we want to start doing some spatial maps and trying to understand what our data looks like. There's been a lot of discussions on this week. We're going to mostly use HVplot. Again, Dylan used this yesterday in the SWISAR tutorial. You could do a simple matplotlib, but it's not very interactive and fun. And if I am going to force myself to learn Python, I want it to be interactive and fun. So look at this. You can do an HV plot here, hover your mouse. Can I zoom in? Okay, yeah, you can zoom in on the Jupyter notebooks. If you're on the non-rendered version, there's just more functionality there. I think sometimes when you zoom in on the non-rendered version, it'll actually, you can see as it gets to finer and finer spatial resolution, it like I don't know what the right word is, but you can really appreciate the much finer spatial resolution as you kind of zoom in and out. This is something that is not going to work in this version, but you can also plot time sliders where you could look through different days. Again, check out the Jupyter Lab if you want to actually make some of these more interactive. And then finally now, actually, wait, let me mention here. So here you can see we're using this one version of the data set, our snow depth at Grand Mesa over water year 2020, and then just data set. And this is for making our spatial map. Now we're going to start thinking about time series. And now you can see we are using that time chunked one instead. So again, I think as we all become more comfortable working with these really large data sets in the cloud, learning these little tricks are going to be important. I'm definitely still learning this, but this has been a nice introduction for me to get a little bit more familiar with this. Let me scoot this to the side so we can see this. So here what we're doing is we're selecting just a single point in our domain and then plotting the time series at that point. So in this figure here, the red dot is where our single point was on Grand Mesa, and then we're plotting a time series of snow depth. That can be helpful for understanding what's going on at a single point, but since we have this nice spatial, these spatial data sets, things like aggregation are really important. Maybe we want to take the mean over the whole area. So you can do that here with just the simple mean function, calculating over our latitude and longitude. When we inspect our data set, you can see now we only have a time dimension, right? Because we've shrunk down our lat and long through our mean. And then when we plot that as an HV plot, we can see, all right, now we can look at our mean snow depth over this whole area. It's not really over just Grand Mesa since our box is larger than that, but you can get the point and appreciate what's going on here. So any questions now, just understanding a little bit about what lists or snow model output might look like before we start thinking about doing any comparisons? Okay, cool. So now let's start thinking about raster to raster or raster to point comparisons. The data set that we want to compare to here is, we'll just grab some SNODAS data. Here again, this is actually just data that's stored on our S3 bucket. You could obviously pull this from NSIDC or wherever, but in this case, I just have it saved in a ZAR file. Again, this is a big file and this really slows things down. It's not the ideal way to do this, but for the purposes of putting together a tutorial, this is what we are working with. So we're going to read in our SNODAS data, and then we're going to write this function that can help us extract the latitude and longitude of our nearest point of interest. So you can see our little description here. And then basically what we want to look at here is really similar to what we already did above when we were only looking at the list data, but now we're also looking at SNODAS. So we want to take this, extract our coordinates of SNODAS to the nearest grid cell for that snow model grid point that we were previously looking at. Then we're going to subset for our dates of interest, and then just plot a time series and compare the performance of snow model versus SNODAS at a single grid point. So again, just walking through this really quick, we're using that nearest grid function. We're selecting our dates of interest. We're selecting our latitude and longitude of interest here. And then we kind of repeat the same thing for our snow model output. And then let's build our HV plot where we are going to have here snow depth over our 6 months of our water year, and then 2 different lines, both of which are interactive. And if you want, you can turn them on and off if you'd only rather see one line. and we can start to understand our model performance. This is a handy tool for just a quick look at how things are doing. How does snow model compare to SNODAS at a single point? Now here, thinking about this, both snow model and SNODAS are models, right? Neither of those are observations. Let's go ahead and pull in an observation. So we're going to grab a SNOTEL point. So again, in this case, I just downloaded the SNOTEL data myself and hosted it on our bucket, but you can definitely just grab it from the web as well. So here is just some functions for helping us read and load in the SNOTEL data. And when we read it in here, we're specifying just Colorado because the Grand Mesa is in Colorado. So let's, for just like, I don't know, data size sake, let's only read in Colorado data. And then a function for reading in just the snow depth associated with the snow pillow. All right, so we can load in our data and we can look at just the first few rows of those, of the SNOTEL record for the first, I guess, 6 stations sorted alphabetically. The latitude and longitude that we've looked at corresponds to this Park Reservoir SNOTEL station that's on Grand Mesa. So let's go ahead and specifically call that one out and pull the snow depths there. So that way we can add it to our plot. And once we do that, we can build our HV plot. We can actually just build off the one that we already made above and add in our Park Reservoir plot here. And now we have our third line. So in yellow, we now have our SNOTEL data. So we can compare snow depths from January 2020 to June of 2020 and see that, you know, they compare pretty well through, oh, whoops, you can also move it all around. They compare pretty well through like April, May-ish, and then they start to have pretty different melt signals towards the end of the season. So then if you'd like to kind of bring all of what we've learned together into one visualization, we have this interactive plot. As it notes here, this is not going to work in this rendered version for the maximum interactivity. So I actually will go ahead and skip to over here. So there's a lot of code here. I somewhat understand it, but not all of the ways. But if you have questions, I'm still happy to go through it with you. But we're basically building up to this widget here that allows us to compare our snow model output, our SNODAS, gridded data assimilation data set, and SNOTEL stations over our full model domain. We can look at SNOTEL sites in Colorado, or we could say, we could pick a different state and load those. Hopefully this is still, yeah, so you can load in the SNOTEL, snow pillow sites from different states. Sorry about that. We'll skip back to Colorado. Hopefully, oh, well, I think my kernel decided to shut down. And as I mentioned, it'll take 10 minutes to run this, but you can get the point that it makes this interactive plot where we can look at different variables like SWE or snow depth, and we can specify that. We could look at different days if we want. Actually, it came back. So let's go ahead and just select a site near Grand Mesa. And then it'll take a minute or so, but then it'll plot our time series over the full water year 2020, comparing these 3 different data sets. And again, you can kind of play around with different parts of the domain, looking at SWE, looking at snow depth. You can see where the model's maybe performing well and where it's performing really, really poorly. And these tools are really important to help us understand the behavior of our models and kind of zero in on areas where we need to really improve our parameterizations, or areas where maybe we're doing better and compare more favorably to observations. Maybe this doesn't want to run. Well, we'll go back to the rendered version. Sorry, I scrolled all over. But yeah, basically you can just click any of the snow pillow sites and it would eventually plot a time series. Sorry, that's moving a little slow for us today. So I think I'm way ahead on time. I put a couple of exercises if anyone wants to just think about this and kind of play around with the code, but we don't need to go through that together. But hopefully this just gives you a good appreciation of what model output, a typical model like a snow model, what it looks like, how you can start interacting with it, and how you can think about how, how can we go about combining this with like the SWISAR data that Dylan presented, or the P-band data that we learned about yesterday, or the LiDAR data, whatever data set. Data assimilation isn't limited to just, one data set at a time. You can do multi-DA, all of this. So yeah, this is just going to be a really important tool moving forward that's going to allow us to bring together a lot of these different observational data sets that we're all kind of working on. So yeah, thanks for listening. If you have any questions, happy to chat. Yeah, HP.
Really well done. I'm just curious, so in this list snow model run, have you done any assimilation?
No assimilation here, just to keep it simpler. Yeah, this would be the open loop. Yeah, exactly. Yeah, SnowDAS is like this little black box that doesn't have great information on it, I think. But yeah, SnowDAS definitely, it assimilates like anything it can seem that it can get its hands on. So it's an assimilated product, but with lots of observations into it. I don't think there's a whole lot of information maybe on the modeling side of SnowDAS. But yeah, still a useful comparison data set. I think this is with NLDAS too. I'd have to double check, but I think that's what I picked. Yeah. But it's pretty it's pretty simple to switch back and forth, especially if you have NASA funding and can get an account on NASA Discover, the supercomputer. All of the data are available there for you. So it's very, very easy to set up lists and get it running. Yeah. Especially as it's being pitched as a tool for this broader use. Yeah. Because I'm really excited about this, but my first thought was, oh, let's bring a nice snowball. That'd be great. And then when I saw it was written in Fortran, yeah. So I would say most climate models are all written in Fortran still. It runs fast, right? And if we're talking about doing a 1 kilometer global simulation with data assimilation, you need to go as fast as you can, especially I guess the thought is, like a future level 4 snow product from a satellite might be a near real-time assimilated product. So you need that going as fast as you can. So I think that's why things are still in Fortran in like the climate and large scale land surface modeling community. I'm not familiar with any talks within the group to switching to anything else. Madi, I'm not sure if you're familiar. Yeah, I haven't heard of any whispers of that. What was that? Sorry. Yeah. Oh, yeah. It is all open source. Like, LIS is available on GitHub, so anyone can download it. It's pretty well documented. What's that? I didn't hear what you said. Oh, yeah. But yeah, it would be a huge effort to translate it to anything else. And I think just because it is so computationally efficient at the moment, it's like, why? You don't, like, if you want to run it, you don't have to read any Fortran. You don't have to touch the code at all if you want to run it. So I think maybe that's why there hasn't been a push to do anything. And then I guess the main users of LIS, I know there's a lot of partners with like the Air Force. They do a lot of their weather modeling through LIS. I guess there just hasn't been interest in changing to anything. Yeah. Yeah. Yeah, Justin. Yeah. Yeah, all of the setup files. Yeah, all of the setup files, it's literally like one file to define your domain and one file to run. Like it's very simple from the user perspective to run it. It just gets more complicated if you want to incorporate a new model into it. But I feel like the people that are incorporating new models don't mind digging through Fortran code, I guess. But yeah, I mean, I think that's a valid criticism that it's not as familiar as maybe if we were talking 25 years ago, more people would be like, yeah, Fortran, but not so much anymore. Yeah. Yeah. Yeah.
And extract those out that we think, hey, why should we should all rewrite, data simulation that runs weather data and utilize.
Yeah.
So we can benefit all from the same base, and then we actually can also compare models.
Yeah. Yeah.
How they fare with the same input.
That's a great question. To that, I would say write a proposal and make it happen. But yeah, the list team is like, if anyone has any questions, it's probably, I don't know how many people, 30 people that work on the list team. And just everyone's always happy to help. So I think there's a lot of always, there's always discussions going on the GitHub forums of users that are like, hey, how do I do this? Someone always gets back pretty quickly. But yeah, I would say some of the code, sure, is maybe not as friendly as some of the languages that most people use. But yeah, I like that. That's a great point. People have been testing trying to get it to run on AWS as well. So that way, that might be easier and then still provide access to the meteorological forcing data sets. Cause I think that's the big hurdle. I don't want to run lists on my local machine because I don't have NLS2 on my local machine and I don't want to download that. But if we can get it running just as quickly on AWS as we can on the NASA Discover supercomputer, then I think that would open up a lot of doors as well for people to use it. Yeah. Yeah, for like if we want a couple snow model with no MP. Yeah, right now it's almost as if it's a data assimilation update where we're like running NOAA MP, and then every step where we get to that snow code, I guess, we then would run snow model at that time step and then kind of just replace the snow. Yeah, yeah. Wouldn't say it's like a direct insertion. Yeah. I haven't run it. I haven't run it with metadata. Micromet has been implemented as well. And now you can actually use Micromet with any other land surface model as well, which I feel like was a really powerful step. So that's really important for the wind redistribution and getting the finer spatial scale winds, I guess. So yeah, I've done some experiments where I run NOAA MP with Micromet. No snow model at all, but just the Micromet component. Yeah. All right. Well, thanks everyone. Thanks for the questions.